In this video, we're going to look at rewriting the integral, the triple integral, in all 6 possible ways. So we're being asked to express this integral of some arbitrary function f dv, where e is the solid bounded by x equal to 2, y equal to 2, z equal to 0, and then x plus y plus 2z equals 2. Alright, so what does the solid look like? Well, here is, of course, z equal to 0 is your xy plane. X equal to 2 is this this grayish, bluish, whatever colored plane. Y equal to 2 is actually over here. I've got this rotated from behind to see what's going on. It's this pinkish one. Here's y equals 2. Your red axis here is the x-axis. The green axis is the y-axis. The plane x plus y minus 2z equals 2, well, that will cross your z-axis down at -1. So it's actually coming up and popping through, if you will, the xy plane here along this line, which is what? X plus y equals 2. And then comes through and hits these two planes over here and over here. So we got this triangular shaped region here that's on the top of the solid. The bottom of the solid would be the xy plane, which is underneath this greenish one. The bluish one here, the bluish gray one here is representing one side of the solid that you can't see. It would be behind this green. And same way with the pink, it would be the other side of the solid there. All right. So if we wanted to integrate this with respect to x first, well, our x would go from the surface defined by the plane, x plus y minus 2z equals 2, to the plane x equal to 2. Well, we would need to describe that plane, then x equals a function of y and z. So we would need to solve for x and get x equals 2 minus y plus 2z. That would be your lower limit of integration for x. The upper limit of integration for x would be 2. Likewise, if we want to integrate with respect to y first, well, we would still have the same plane being our lower limit of integration, because we would be going from the plane to the from the green plane to the pink plane. We would just need to solve for y in that case and get 2 minus x plus 2z, and then the upper limit of integration would be 2. Finally, if we wanted to integrate with respect to z first, your lower limit of integration would be 0, because that's the xy plane, and then it goes up to the green plane. Solving for z, you would get 1/2 of x plus y minus 2. And we see that reflected here in the 6 iterated integrals that we have over here. Here we're integrating with respect to x first, so we have the lower limit for x, the upper limit for x. These two we're integrating with respect to y first. We have the lower limit for y, the upper limit for y. Likewise, we have integrating with respect to z first. I'm missing a divided by sign. There should be a divided by sign right here after that right parenthesis. We've got lower limit of z, upper limit of z. And again, just likewise, there should be a divided by sign there. I apologize for the typo. All right, if we've integrated with respect to x first, then we need to project everything onto the yz plane. If we do that, then we can see it's basically this triangle here, where you would have z equal to 0 for one bound, y equal to 2 for another bound, and then the equation of that line in the yz plane, which would be y minus 2z equals 0. Likewise, if we project onto the xz plane, that's essentially what looks like on this pink plane here, except it would be on the plane. We would have z equals 0, x equals 2, and then the equation of this line moved over here, which would be x minus 2z equals 0. Again, you can see that pretty easily just by plugging in 0 and for the appropriate variable here to get the equation of the line that I'm talking about. Finally, if we project down into the xy plane, we've got y equals 2 and x equal to 2 as part of our bounds, and then this line has the equation x plus y equals 2, again plugging in 0 for z. So if we integrated with respect to y and then z in that regards, so your y would equal 2z, would be your lower bound, and your 2 would be your upper bound, and your z's are going from 0 to 1. If we flip it around, solve for z here, your lower bound would be 0, your upper bound would be y over 2, solving this equation for z. Then then your your y's would go from 0 to 2, and this would be your limits. And then you can see in the other 4, that's exactly how we're describing those regions. So for this one, I forgot to flip my order of limits of my order of my integration here. This should be dz dx here. For this one, notice we've described it in terms of x, and then with returns in terms of z. This one would be in terms of z and then in terms of x. So this should be dz dx here. I forgot to flip the order of limit integration. But you can see that these other 4 the other 4 integrals here, you can see how we're describing those regions based on how they look in the respective coordinate planes.